Welcome back, 12th graders. It's Mr. Klinkerman. You know you're in Klinkerland once again. We are today trying to find the higher order derivatives of a function. We're in section 7.4, which started with the chain rule and now is continuing with higher order derivatives. One thing I want you to notice is that every time I do a video from now on, I'm going to write the learning goal or the learning goals for the section that we're trying to learn on the screen at the beginning. And here you can see that what we're trying to do is we're trying to learn how to find a higher order derivative. You will be able to find a higher order derivative of a function. And quite simply, when you're trying to find the higher order derivative of a function, you're trying to find its second derivative, or the third derivative, or the 90,000th derivative. Guess what? We're never actually going to find a 90,000th derivative, but the concept is a pretty simple one nonetheless. Alright, now along with teaching you how to find a higher order derivative, I would like to teach you the notation that you're going to use to indicate that you're finding the second or third derivative of a function. And I'd like to show you the meaning behind what you are finding if you find the second derivative of a function. You know the meaning of the first derivative of a function is that it's the slope of a tangent line at a certain point on a graph. Alright, you're going to learn the meaning behind the second derivative, or at least a basic meaning to start off. Let's go ahead and talk about the notation next. If you have a function that you notate as f of x, you know that quite simply to indicate that you're finding the first derivative of that function, that you're going to write f prime of x. And it follows that you're going to use f double prime of x to indicate you're writing a second derivative. You're going to use f triple prime of x to indicate you're finding a third derivative, and so forth. Of course, you can also write functions not in function notation form where it's f of x equals something, but as y equals some function. And when you write a function in that form, we've said that you can write the derivative of that function using the notation dy dx. Alright, now this notation isn't what you might expect, but for the second derivative, simply what you're going to do is you're going to write that it's equal to d2y over dx squared. Now, where in the world does that come from? If you simply think about taking dy dx and then taking the derivative of that with respect to x, you can see how you get d times dy essentially gives you d2y over dx squared. Now, we're not putting a 2 after the d this time, but we will put it after the x squared. It's just the standard notation. You'll get used to it. And so then the notation for the third derivative, you'll put d3y over dx cubed, and so forth. Alright, that's notation. Now let's take a look at a graph of a function so I can explain to you what you're doing when you find a second derivative. What you're looking at right now is the graph of the function f of x equals x cubed minus x squared minus 6x, as you see the equation written on the screen. Now, what I'm going to do really quickly is just show you how do you find the first derivative and the second derivative. Of course, the first derivative of that function would be 3x squared minus 2x minus 6. And you guys know that if you wanted to use that equation, you could use it to find the slope of the derivative, the slope of the function at any given point. Well, we want to know what it means to find the second derivative of a function. And it's really easy to find the second derivative. I'm just going to take the derivative of f prime of x. And I could just use the power rule here to do that. We'll get f double prime of x equals 6x minus 2. Okay, now I need to explain a concept right here. When we're dealing with the second derivative, rather than telling you something about the slope, what it's going to do is tell you something about the concavity of a function. For instance, if you look at this function over this interval right here, what you're going to notice is that this graph is what's called concave down, meaning it looks like a parabola and it's opening downward at that point. Whereas if you look at the function over this interval, you're going to see that it's concave up. It looks like a parabola opening up at that point. Alright, so you got concave down, you got concave up. Now let me show you how the second derivative works. Let's suppose that I wanted to find the value of the second derivative of the function when x equals -1. Or in other words, I want to look at this point right over here, and I want to know, is this graph concave up or is it concave down at that point? Well, when I plug in -1 for x, you can see I'm going to get 6 times -1 minus 2, or in other words, I'm going to get -8. And it works very easily. Since the second derivative had a negative value at -1, that means the graph is concave down when x equals -1, which matches what we talked about earlier. Now you might also notice the slope of the tangent line would be negative at that point, but that's not what the second derivative tells you. Let's also suppose that we wanted to find out what the concavity of the graph was when x equals +1. Kind of hard to make dots here. There we go. If I find out the value of the second derivative of x equals +1, well, it's going to give me 6 times 1 minus 2, or it's going to give me 4. And so what that tells me then is the graph is concave up when x is equal to +1, which is what I had shown you earlier when I highlighted that portion of the graph. Now I told you this was separate from the slope of the tangent line. You notice the slope of the tangent line is still negative, but that doesn't mean the graph can't be concave up at that point, and in fact it is. Great, that's the meaning behind the second derivative. Well, let's take a look at a couple examples where simply all we're trying to do is find a second derivative or a third derivative and so forth of the function. And you see the function that we're going to work with here. And I want you to notice that this function is going to make use of the product rule, because we just have simply 3 minus 4x cubed times e to the x. And we're trying to find d2b over dm2, dm squared, however you want to say that, which means we're trying to find the second derivative of the function. Alright, well, let's start off with the first derivative, which would be the derivative of b with respect to m. And since we are doing the product rule, we're going to do the first function times the derivative of the second, 3 minus 4x cubed times e to the x, because it is its own derivative, plus the second function times the derivative of the first. And the derivative of the first function is simply -12x squared. Alright, fairly simple, isn't it? One thing I'm going to do here is I'm going to make this look a little neater so that when I take the second derivative, it's going to be nicer to work with. You notice how e to the x is a factor for each of these two terms? I'm going to factor out the e to the x, and that's going to leave me with 3 minus 4x cubed minus 12x squared, which I'm then going to rewrite as e to the x times -4x cubed minus 12x squared plus 3. Now let's take that and then find the second derivative of the function, or d2b over dm2. Again, product rule here. The first function times the derivative of the second, which is -12x squared minus 24x, plus the second function times the derivative of the first function, which is just e to the x. Hoping you guys can see that stuff over there. Alright, now once again I've got e to the x as a factor of each of these terms that we've just created, so I'm going to bring it to the front just to make this a little nicer to look at. And then that's going to leave us with -12x squared minus 24x minus 4x cubed minus 12x squared plus 3. And there's a couple of like terms that we can combine there. I'll write the highest order term first, -4x cubed, e to the x times -4x cubed minus 24x squared minus 24x plus 3. It really wasn't that tough, it was just applying a derivative twice, right? Let's try the next example. Now here we're trying to find a third derivative, and what I would actually like is for you guys to pause the video and to try to find this third derivative on your own, and make sure that you make use of the chain rule in order to do so. Alright, pause it now, then start it up, see how you did. Let's see how you did. Remember that whenever you're using the chain rule to find the derivative of a function, you do the derivative of the outer function times the derivative of the inner function. And the outer function here being ln of x essentially. And the derivative of that being 1 over x, so you have 1 over x squared. And then we're going to multiply that by the derivative of the inner function, and the derivative of the inner function is 2x. You can do a little canceling here with the x and with the x squared, and it leaves you a 2 over x or 2x to the negative first power. And then of course it's easy enough to go on and say that the second derivative, f double prime of x, is equal to negative 2x to the negative second power, which you can write like that, or you can write it as negative 2 over x squared. Up to you. Good job. One more to try, same drill. I just need to teach you one little bit of notation that I want you to try it on your own. And the bit of notation that I want to show you is simply that whenever you're told to find a derivative and then at the end of it you have this vertical line with a value, it means that once you find the corresponding derivative, you're supposed to go ahead then and evaluate the derivative for that value of your independent variable. Now I'm noticing here that I put d2v over dr cubed. That's supposed to be d3v over dr cubed. So I am asking you to find a third derivative here and then evaluate that for when r equals 5. Pause the video, try it out, see how you did. Alright, it was very easy to find the derivatives here. All you had to do was use the power rule a few times. Remember, pi is not a variable, it's just a constant. So the first derivative gives you 4 pi r squared. Second derivative then gives you 8 pi r. The third derivative gives you 8 pi. Now, that means that whenever we're trying to find d3v of dr cubed when r is equal to 5, well, there is no value of r to replace with 5, and so it's actually still equal to 8 pi. But suppose that it had still been 8 pi r like the second derivative was, then you would have substituted 5 in for r, and you would have found the value that you're looking for. Hope this helps out a lot with higher order derivatives. We're going to practice some more in class tomorrow. I will see you then. Good luck. Thanks.